Alright, it's going to be another Codeforces editorial here for round 883, Division 3, contest ID 1846. I'm going to gloss over the problem statements. This document will be linked in the description, this text document, as well as submission links for all my Codeforces implementations. So first problem, Rudolph and cut the rope. The ith nail / rope allow the candy to fall down to some height equal to AI minus BI. So the height of the nail minus the length of the rope is where the candy can fall. Before we cut any ropes, the candy rests at Hmax. So what that is whatever the maximum value of this is for all the ropes and nails. So if we go here, initially, so for this it's 1, for this it's 2, for this it's -1. So initially our candy is resting at height 2, since that's the maximum value of AI minus BI. Now in order to get the candy to the ground, we need Hmax to get down to 0 or less, since this rope and this nail, this one in this picture, it only lets the candy fall down this far. So we need to cut any rope where this value h is greater than 0. So if the rope is shorter than the height its nail is at, so we can see here we need to cut this one because the rope is only 1, but it's at height 3, so our candy can only drop to 2, and we need to cut this one since the nail is at height 4, but the rope only drops down to height 1. So these two will both keep our candy from getting down to the ground, so we need to cut these two. So we simply iterate over all these pairs, find this difference, so just subtracting these two, and then every time we find a rope that meets those requirements, we add it to our count, and then simply return the count at the end. So this is the implementation. Actually, this could be implemented even more efficiently, since right now this implementation that I have stores all the AI and BI, but you could just read in AI and BI here and increment the count instead of storing all of them. So this actually is not the most efficient. I'll update that for my Codeforces submission, so it's optimized. But yeah, we just check h and then increment our count output. So that can be done in O of n times. So we need to look at all the ropes and nails, but it can be done in constant space, like I said, since we don't actually need to do this storing. So I'll update the final submission that's linked in this document. Next problem, Rudolph and Tic-Tac-Toe. So we know that the board is 3x3, which means that we can just brute force and check all the rows, columns, and diagonals with brute force, since if a player won the game, we'll find either a row, a column, or a diagonal that's full of that player's symbol. The only exception is if the row, column, or diagonal is full of periods. So like this is an example where this doesn't mean a player won, since these represent empty spaces. So if we come across like a column or row like this, then we just continue on. But if we ever find a row, column, or diagonal for the same symbol that's not periods, then we're done, and that the player with that symbol is the winner. So here, as soon as we find this row, we're done. We can just output plus. or for here, as soon as we find this diagonal, we're done. Can output 0 or O. And if we check all the rows, columns, and diagonals and don't find a winner, then the game was a draw. So like in this scenario, we check everything and we don't find a winner, that means the game was a draw. So I'll pull up my code for this problem. So here I'm checking all the rows. So my iterator is on the row part of my board, and if it's a period, I know that the row, column, and diagonal containing this index is not going to be part of a row, column, or diagonal that is a winner. So, but if it's not a period, I check that all three indices in this row are the same. If they are, then I output whatever symbol's there. Same with columns. Check that every row in this column are the same symbol. Diagonals, same thing. And then if we get to this point without finding a winner, we just mark it as a draw. So this can be done in O of 1 time, since the size of the board is fixed. If the board was some arbitrary size n by m, then our runtime would be O mn, since we have to look at the whole board. It would depend on the rules of that board. If that board was like not square, then maybe there's different rules. But we can also do this in O1 space, since the board is fixed. Again, if the board was n by m, our space would be mn. Since it's convenient to store the whole board, there's probably some way to do it where we only look at one row at a time, so we only have to store one row at a time. There's probably some way to do that, so we could probably get away with OM, but in this case, since the board size is fixed, it's just constant space. Okay. Rudolph and another competition, problem C. So the first thing we want to observe is that the optimal order to solve problems in is the order shortest time to longest. So using this example they give us, if this is our order, it's optimal to solve the problem that takes 15 minutes, then the problem that takes 20 minutes, then the problem that takes 110 minutes. And the reason why that is the sum, or the penalty associated with each problem is the sum of the time it takes to solve it plus the time it took to solve all the problems that we solved before it. So they give a pretty they demonstrate that here with this example, so you can read that if you want an explanation of why this is optimal. I think it's pretty intuitive, so I won't go more into it. But another reason why this is the case is all the problems have the same value. They all count as just 1 point. So we just want to solve as many as possible. May as well solve the easy ones first, the ones that take the shortest time. So in order to calculate the score, which is the number of problems solved, and the penalty for each participant, we sort their information. So we sort. So for this participant, which is Rudolph, we sort this list. Then for this participant, we sort this. It's already sorted, and then we sort this. And that's so we can see which problems take them the shortest amount of time, according to our optimal strategy up here. So once we sort it, then we go left to right, and we keep going until the sum of time that we've spent on problems exceeds the duration of the contest. So we have time limit of h minutes. So if it's 120, once this would be sorted, we would do 15 first, then 20. Then we would have enough time to start attempting the problem that takes 110 minutes, but we wouldn't finish it. So in this case, we would go 15, 35, 145. Okay, 145 is over 120. We just count the first two problems. So that's how we calculate the score of a participant, and then their penalty would be the number of problems, the sum of time it took them to do the actual problem. So uh, 15 plus 20, or 15 plus 35, since we would do the first problem 15 minutes, then the second problem would be done at 35 minutes. So 15 plus 35, 50. That would be our penalty. 2 problems solved, 50 penalty. So now that we know how to calculate the score and the penalty for every participant, we'll go through the participants one at a time. And we start here. This is Rudolph's information. So we'll calculate his score and penalty. We just found that is 2 problem solved and 50 penalty. And we'll keep track of that, as well as his rank. So initially his rank is 1, because he's the only person that we've calculated this for so far. Then as we go down each row, we sort this. In this case it's already sorted, but we go 90, 90, this is exceeded. So they only solve 1 problem with penalty 90. And we compare that to Rudolph. And according to the contest rules, I'm not going to read through this whole thing, but we check the score first. If that's tied, then we go to the penalty. If that's tied, then Rudolph is given precedence. So in this case, this participant did not outperform Rudolph, so Rudolph stays number 1 for now. Then down here, we go, okay, this participant solved all 3 problems with 280 penalty, I think. 40 plus 80 plus 120, 240 penalty. So because he has a higher score than Rudolph, he outperforms him and knocks Rudolph down to 2nd place. That's why we increment Rudolph's placing when he gets outperformed by a participant. So then we're at the end of the list. Rudolph's placing is 2, output 2. I'll pull up my code for this. So we read in our stuff here. Once again, same with my submission for A. I guess we don't actually have to store all of the information. We can go one row at a time. So we can find this for Rudolph, store just his penalty and score, then read in this row, update Rudolph's placing necessary. Same with this. So storing it here is actually unnecessary, but the gist of it is we read in a row, we sort it, then we iterate over their list of solution times, and we keep, if they can solve the next problem in time, we add a point to their score since they solved that problem within the time limit, as well as add the appropriate penalty to their penalty. And this is just to keep track of how much time they have left. So we go over that, we get their points, we get their penalty, and yeah, I guess we don't actually have to store it, but we compare it to Rudolph's points and penalty, and then update his placing if necessary. So I'll update this code as well, since we don't need this. The storage is unnecessary. Excuse me. So the runtime for this is nm log m. The reason why that is because there's m entries on each line. We have to sort, and there's n lines. So sorting one line takes m log m, and there's n lines for us to sort. So nm log m. om space, we need to store the list of solution times for each participant for when we sort it. So we only need to store 1 row at a time. So this code stores all of them, but we only need 1 row at a time. So I'll update that, because we can reuse the space for the next participant once we've calculated their score and their penalty. We don't need to store their data for any longer than that. Alright, problem D, Christmas tree. The first thing we're going to do is we need to find how much of each branch is exposed. So for this branch, it's 2. The entire height is exposed. For this one, it's only 1, since the from height 1 to 2 of this branch is covered by the next branch above it. So in order to find out how much is exposed, we will iterate over the heights of the branches, and if the height of any 2 consecutive branches is less than h, the second branch will partially cover the first branch. So in this example, so this branch starts at 4, this branch starts at 5. 5 minus 4 is 1, which is less than the height of 2. So that means the branch that starts at 4 is partially covered. So its exposed height is only 1. So we calculate the area. So I think I call this UI, exposed as uncovered. So U. And we need to calculate the area of each branch based on its uncovered portion. So based on the height of the uncovered portion, we can actually calculate the area. So initially we just need to find this uncovered height, because that gives us all the information we need to find the area of each segment of the tree. So maybe it'll be easier actually to walk through this if I pull up my code. So the first thing we do is we read in the starting heights, or the branch locations, and if some branch is covered at all by the next branch, then we mark how much is uncovered. If it's not covered at all, then the default value is just the full height of the branch. So then we iterate over all the uncovered parts of the branch. If it's fully uncovered, which means that the uncovered part is height h, its full height, we can just use the basic triangle area formula to add to our sum. I move on to the next one. If it's not, then what we can do is we can take the full area and subtract the covered area from it. So if we have like something like this, and let's say, so this part of the blue branch is covered. This part that's somewhat filled in. What we can do is, instead of calculating this area here, this trapezoid, we can just use our triangle formula to calculate the entire area of this blue triangle and then subtract this covered area, since they would both use the same formula. So the height of the covered part of the triangle is h minus ui, and that's because ui is this uncovered part, and then h is the total height of the branch, covered and uncovered. So this is our height. I'll call this HC, or what do I call it in the program? Covered H. And then now we need to find the base length, so we need to find this length. The base of the covered part is whatever fraction of the height is covered times the full base. So if it wasn't uncovered at all, then our base would be this. But if half the height of our triangle is covered, so let's say h is 2, and then this is 1, and then this whole base is d, this base is d over 2 because half our height is covered. So our base is half the length as well. So the base, and I'm using d as the base since that's what it is in the original problem statement. This is d times the fraction that's covered. The fraction that's covered is this. H minus ui over the total height. So then to find the area of this triangle, the covered part, this triangle here, we can do height minus base, or height times base over 2. But that's just the area of this covered part, and we wanted to find the area of the uncovered part. So the total area is this. Subtract the covered part. And this is what we want. Whatever this is, we want to add this to our sum. So exposed area, add this to our sum at the end, print it out with, this is just some decimal formatting since the problem gives us some error of 10 to the minus 6, so we output 6 decimal places in order to meet that error. So that's a visual explanation of this problem. So we can do this in linear time, however many branches there are. We just need to make a couple quick calculations for each branch. So O of n time. O of n space, since we store all the branch locations, it's probably possible to do this in O of 1 space by only storing 1 or 2 branches at a time, since you only need to look at this branch and the next branch to see how much is covered. I won't update my code for that, but maybe I will. It's only a small change. I might update the code to use O1 space. We'll see. So yeah. E1, Rudolph and the Snowflakes. So this is the simple version, and for the simple version, I'll show a solution that won't work on the hard version because this solution is much easier. When I get to the hard version of this problem, I will show why this solution does not work, and then I'll give the solution for the hard version. The solution for the hard version will work on both versions, so if you just want to see that, then go ahead and skip ahead or read ahead to find that. So based on the problem statement, we begin with one vertex, add k, then add k squared. Then if we want, we can add k cubed, k to the fourth, etc., etc. But we're only required to do these steps. So we can brute force this problem, checking all k starting at 2 up to square root n. So we start with 2, try if that works, try k equals 3, see if that works, on and on until square root n. And we know square root, we won't have to go past that, because if k is greater than square root n, then k squared, which we're required to add, will be greater than n, which is the total number of vertices in our snowflake. So that's not possible. It won't be possible for us to go past square root n. So to do this, we will initialize our total as 1, the center of the snowflake, and then we will continually add powers of k, k squared, k cubed, until our sum reaches or exceeds n. If our sum lands on exactly n, then we answer yes, because we found a k that works. And if it exceeds n, then we know this value of k doesn't work, so we go to the next value of k and try again. So this is our initial or our starting point. We add k, we increment the amount we're adding, or we increase the amount we're adding from k to k squared. So add goes from k to k squared, we add this, And these are the required steps. So current at this point will be our minimum number of nodes or vertices with this value of k. 1 plus k squared. And from now we can try adding k cubed, k to the 4, k to the 5. And once we meet or exceed n, we check if we got exactly n, then we're done. If not, then this value of k is invalid, so we go to the next one up until square root n, so k times k is n. And if we reach square root n without finding an answer, then the answer is no, there's no possible solution for k. So the runtime for this is square root n log n. This is because we will try up to square root n different values for k, and each attempt takes log n time. So one iteration of this loop takes log n time, and the reason that is because we're incrementing current by k squared, k cubed every time we run this loop, and the highest we can go is k to the log n, because k to the log n equals n. So we'll never go past, our power will never go past log n. So this entire body of the loop takes at most log n time. And we'll run it square root n up to square root n times, so we get square root n log n. In reality, the square root n portion is much more important, since the log n grows much slower. Storage, we're not really storing anything, just these iterator variables and our sum, so we can do it in content space. Now on to the hard solution. So the reason why this solution doesn't work for the hard version is that the constraint on n is much weaker. In other words, we can have all the way up to 10 to the 18. And with our previous implementation, which runs in square root n log n, let's just ignore this and assume our solution can be run in square root n. In reality, it's worse, but we'll assume it's this. In the hard problem, n can be up to 10 to the 18, which means square root n is 10 to the 9. We only have time for about, actually we only have time because we have 2 seconds. Actually, wait, this is right, no. So we have time for 2e to the 7, 2e7 operations, but we don't have time for that, not even close. So we need to come up with a different approach entirely. So this video will contain some whiteboard math that I'll do on screen here. It'll be quickly summarized in this document here, but it won't go too much into detail. So if reading this document is confusing, make sure to check out the next few minutes of this video. So instead of iterating over k, let's iterate over p. What do I mean by p? So essentially what we're doing with the snowflake is we're starting with 1, or k to the 0 basically, then k to the 1, k to the 2, k to the 3, up until k to the p. So we'll call the last power p that we're using. And we're going to iterate over p. So we're going to try different values of p starting at 2, since we're required to add k to the 2 vertices to the outer layer of the snowflake at least. And we will go up to 60, since 2 to the 60 is greater than the maximum value of n. So if we go up to, if k is the minimum value, has a minimum value of 2, if we go up to p equals 60, this is guaranteed to be true. So we don't have to go past 60. So now that we have our iteration range 2 to 60, how can we check if these values of k and p are valid? So we will go to this, and I guess, like I said, this can be 60. I'm not going to change it, but this in reality can be 60 because 2 to the 60 is already greater than 1e18. Anyway, we take the pth root of k and we round down. And if k is less than 2, this value of k, or this value of p will not work. And in fact, we can just say that we're done and no value of p will work, because future values of p, since we're iterating upwards, k will only continue to decrease for each value of p. As p goes up, we're taking a lower power of n, so k won't get any bigger. So the answer in all future iterations will also be, or k in all future iterations will also be less than 2. So if k ever is less than 2, we're done. The answer is no. But let's take the case where k is at least 2. We can check this formula to see if our values of k and p solve for this. And this is where I'm going to explain here with the math. So if our value of k and p are valid, this statement will be true. Now, I'm going to multiply both sides by k. So 1 goes to k goes to k squared, etc., up until k to the p plus 1. And we are multiplying this side by k as well, so kn. Now, if we go back up to here, this whole left side equals n, which means that if we move this 1 over to the right side, we get this. Now, if we multiply or if we add n minus 1 to, or yes, okay. So this portion of this summation, since we incremented 1 k squared, k cubed, k fourth, k to the fourth, k to the fifth, all the way up until kp, that means the first p minus 1 terms will be this, because this last term got multiplied by k to get to this term. So that means this whole term is n minus 1, which we already established here. So that means n minus 1 plus this term, because this whole term is n minus 1, plus this last term equals kn. Right, because this whole left-hand side, except for this term, is equal to n minus 1, which we established using the first equation. So we're down here now. Now, if we can subtract this n over to the other side, so we get k to the p plus 1 minus 1 equals kn minus n. Drag the n out, and we're left with this. So now we can easily verify with our program if k to the p plus 1 minus 1 equals n times k minus 1. If those two are exactly the same, that means we found a working k and a working p. So then we found the answer, we can just return yes. Now to the runtime for this, it's just log n, since we iterate up to p such that 2 to the p equals n. That's what we were saying at the beginning, right? We only have to go up to 60 for p, and that's because log 2 of n is 60. So p will never exceed log n. So O log n, and the calculations we have to do within each iteration of p are constant and quite minimal. So O log n runtime, and as in the previous version, we don't need to store anything, so no storage. Once again, this solution will also work for uh, the easy version. Although if you wanted to maximize efficiency, you could trim this down to 10 to the 6 is about 20, I think. 2 to the 20, so you could reduce this down to 2 to the 20. You would get the same answer, but once you get up to 20 on the simple version, you don't have to check anything past that, because if you don't find an answer by 20, 21, 22, up to 60 or 63 or whatever won't give you an answer either. Alright, next problem. So this is an interactive problem, which means that your code will do more than just read the initial input and then spit out an answer. The jury will continue to give you input based on what your program outputs earlier in the problem. So if you don't know about this type of problem, this link on Codeforces is a guide for that they've put out. So you can read that to better understand the interactive task. But moving on, we have 5 chances to find a mimic. So 5 options. So that means, and that includes giving our final answer. So by the time we walk into the room the 5th time and look at the objects in the room, we have to know our answer. So the key strategy in this problem is to count the number of each object in the room on every visit and compare this count to the count of our previous visit, and compare them and see what's changed. See if the mimic has changed form since our last visit. So on our first visit, we always have to take our counts and then leave without discarding anything, since we have no information. We don't know what the mimic was before we came into the room, so we can't know what shape it is now. But beginning on the second attempt, we can take our count and compare it to the previous count. By the way, when I say count in this problem, it means we keep track of a count of each type of object. So for this one, type 1 has 2 objects, type 2 has 2 objects, type 3 has 1 object. So you would keep in the dictionary or a map or something the count, the frequency of each type. So beginning on our second attempt, we can, now that we have some previous information from our first visit, we can take our count and compare it to our previous count. If it's changed, obviously that means the mimic has changed form. And we can look at the type, so that means some object type has increased since the mimic changed from some type to another type. The type it is now, that count has increased since the last time. So we know that one of the objects of this type that's increased is the mimic, which means that we can discard all objects that are not of this type. So in this example, well, this is a poor example because I think this output shows a strategy that doesn't work. But let's say this example. So this is initially we have two of each type, yeah. And then we leave the room, come back, and now we have 3 3s but only 1 1. So that means now the mimic is one of these 3s. So that means we can throw away the 4. We can throw away all 4s, all 2s, and all 1s. So yeah, this doesn't show the optimal strategy, but that means we would throw away object ID 1, object ID 3, 5, 6, and 7. So after we've done our discards, so then we would only have 3 3s left. After we've done our discards, we simply wait until the mimic changes again. Because as soon as it changes, obviously the other 2 objects are not going to change. As soon as it changes from a 3 into something else, we know that whatever object changed is our mimic, since the only remaining objects are this type. The mimic will be the only one of a different type, and then we can give our answer easy. So In other words, the mimic starts in some form A. We don't know what A is. We wait until the mimic shapeshifts and changes into some form B. And when it changes to some form B, we'll know what B is, since the amount of B's in the room increased. Next, we discard all objects that are not of type B. So in this problem, the mimic changed from A, which was some object we don't know. Actually, we do know. It was 1, but now it's changed into 3. So we discard all things that aren't 3, and then we wait until the mimic shapeshifts again, and at some point it'll change into something other than a 3, and since everything else is a 3, we've found a mimic. Now we can guarantee this will only take 5 visits because the mimic can't stay in form for more than 2 visits in a row. In other words, by the time we visit the 3rd time, the mimic has to have changed shape, if it didn't already. And once it changes shape 1 time, we can perform our discards in this step here. So worst case scenario, we can do our discards on our 3rd visit. And in the worst case scenario, the mimic changes to something before our 3rd visit. We do our discards. On our 4th visit, we come back. The mimic hasn't changed, so we have to leave since we don't. It could be any of those objects. And then on our 5th visit, when we come back, the mimic has to have changed by now, and then it's revealed itself. So our 5th visit is the worst case scenario, which fits our requirement of 5 queries. So we can eliminate all objects except for 1 type during visit 3. That's whatever form B the mimic has chosen. And then on the 5th visit, we can pinpoint the mimic since it'll have revealed itself by then. So time is O of n. We need to look at the objects in the room, all n objects in the room, or all remaining objects in the room every time we visit, which could be on the order of n. The number of visits is bounded by 5, so our time is O of n. If the number of attempts was higher, it wouldn't matter since we can always we've shown that we can always answer within 5 visits. So our runtime is always O of n. If n and a max, so there's a max is 9, that means there's only 9 types. If both n and a max, so if there were like 200 different types of objects, or a million different types of objects and a million different objects in the room, then we would use a map to update and look at the counts faster, and that would turn our runtime into n log n, since insertion for a map is log n, and we would have to insert n items up to n items. So our space is O1. We don't need to store anything aside from our map, and since the size of the map is bounded by a very small number, 9, we have constant space. We can use a short array or vector as well. If in a different scenario, if there were n object types, our space would be O of n, since we would need to keep track of the count for each object type. I will update. This is the code that I originally submitted and got accepted after the contest, but I will update this since this is kind of a mess and difficult to read. I'll update with a cleaner version of this. So check this text doc after this video gets uploaded, and it will have an updated implementation. Last problem, problem G. So Rudolph's current condition, no matter where we are, whether it's the initial condition or after we've taken some medicines, is some bit string, and that can be thought of as a state where he has some symptoms. Since there are at most 10 symptoms, we can enumerate all possible states in a graph with at most 2 to the 10, about 1,000 vertices. And of course, our goal is to reach a state with no symptoms, which is state 0, or the bit string represented by the bit string with all zeros. So to build our graph, so we already have our vertices in our graph. So now we need to draw the edges. So in order to draw the edges, we will iterate over all the medicines and then draw our edges accordingly. Since each medicine will change, each medicine has the potential to change our state, we're going to have to draw, for each medicine, we're going to have to draw an edge on each node, or each vertex, state, whatever, all interchangeable in this problem. So on a bitwise level, the logic for drawing our edges, Rudolph will have symptom I if and only if he had it before and the medicine does not remove it, or if the medicine causes it as a side effect. So I think this is pretty intuitive, but if the medicine causes a side effect, we will definitely have that symptom. So that's this part of the statement taken care of. If we have the medicine causes it as a side effect, we'll definitely have it. If the medicine does not cause it as a side effect, the only way we have it is if we had it before and the medicine doesn't cure it. Because if we had it and the medicine cured it, then we wouldn't have it. And obviously, if we didn't have it before, the medicine is only going to we're only going to have it afterwards if it's a side effect. So we can write the logic of our symptom removal as old state and not cured, basically, or it gets added as a side effect. So there will be an edge E between vertices U and V if there is some medicine that will cause Rudolph to go from state U to state V. That edge's weight will be the number of days Rudolph will have to take the medicine for. So that's the amount of time it takes us to go from state U to state V. So we iterate over all vertices U and draw an edge between U and V, where V is the new state, which the equation here, we found that up here. And we have to do this for every medicine. Now that we have our graph, we need to find the shortest path from our initial state to the fully cured state, if one exists. To this, we can simply run Dijkstra's algorithm. There's tons and tons of resources out there about Dijkstra, so I won't go into the steps, but I will explain how the global data structures I've chosen help facilitate Dijkstra's algorithm. So this is our graph. I chose an adjacency list since in the worst case scenario we have n equals 10, 1,024 nodes, and m is 1,000. 1,000, actually I'm wrong on this. It should be an adjacency matrix since we have 1,000 medicines, but each medicine can draw one edge per vertex. So we could have actually m times n edges. So this should actually be a adjacency matrix. So I'll update that. I guess the rest of this is irrelevant if we choose an adjacency matrix. So I'll update the code and the doc to reflect that. Next structure, the distance keeps track of our shortest path so far to each state. So this vector keeps track of whether we visited a node so far and confirmed the shortest path, and then this set keeps track of the best paths we found for unvisited nodes so far. So for nodes where we haven't found the shortest path, this contains the shortest path we found for them so far. And the really important part about this structure is that we can easily pick the unvisited node with the shortest path so far, which is always the next step in Dijkstra's algorithm. So our runtime is the quantity m plus n times 2 to the n. That's because we need O of m times 2 to the n time, since we have 2 to the n vertices and m medicines, and like I said, each medicine draws one edge per per vertex. So every medicine draws 1 edge per vertex. So that takes O(m) times 2 to the n time, and then we have to run Dijkstra's. So Dijkstra's takes EV log V time. E is the number of edges, V is the number of vertices. Like we said before, we have m times 2 to the n edges, and V is 2 to the n vertices. So we have m times 2 to the n plus 2 to the n log n, or 2 to the n log 2 to the n. Log 2 to the n simplifies to n. Simple logarithmic rule there. So then we have this quantity here. Pull out the 2 to the n, where we end up with this. I won't go into the runtime on Dijkstra's. Again, there's tons of resources about Dijkstra's out there, so go have a look at that. And then the space required is m times 2 to the n, since we could have this many edges, and then the rest of our data structures are O of v, which is to the n. So that simplifies our total space to this. So I'll make all the necessary updates to the implementations as well as this document. That will be linked in the description, and hopefully this was helpful.